Hey class, Adam Ward here. Want to continue on our exploration of short-term storage analyses. And in particular, we're going to look at something called the StorAge selection function. I know that's not a typo. We're using a capital A because this is an analysis that we're borrowing from the folks who think about age of water in catchments or on landscapes. For those who get really interested in this topic, if you're watching this on HydroLearn, there's a complementary module that's all about the StorAge selection process by Kieran Harmon, who is presently up at Johns Hopkins University. And he will teach you more than I will in this short video, so you can really understand this. What you'll get here is just the bare bones that you need to apply this analysis to your solute tracer studies. With that, let's dive in. So, StorAge selection function. Before we do the math, let's do a bit of an analogous exercise. How do you eat a stack of pancakes? And we have to imagine that we start with a stack of blue pancakes here on our plate. You take a bite, represented by the orange being removed from the system. And as soon as you take a bite, your waiter hustles over and lays a nice, fresh, brand new crepe on top. And it is exactly equivalent to the amount you just ate. So in other words, every time you take a bite, new pancake replaces that bite, and it just gets slapped down on top of the stack. And so the question you have to ask yourself is, how am I going to eat pancakes here? Right? And there are perhaps a few ways to deal with this steady state pancake problem that you have. Right? Every time you take pancake away, it's equally replaced. So somebody out there is saying, I know exactly how I'm going to eat these pancakes. I'm going to eat the oldest ones first. So that's a strategy by which you think to yourself, okay, crepes go on top, I'm going to eat off the bottom. So I'll always eat the oldest pancake. That way the food on my plate never gets cold, it never gets rubbery. I'm always eating from the bottom and fresh ones are coming in on the top, right? Now, somebody else out there might say to themselves, well, that's not what I would do. Why would you not eat a fresh, brand new crepe when it appears? So I'm never going to touch the bottom pancake. Every time a crepe gets put down, I'm going to eat it. So all the old pancakes remain sitting there, and you're just operating by eating this top bite and having it get replaced. And there are an infinite number of strategies in between, where you might think, well, I'll eat mostly fresh pancake, but just a little bit of old, so that eventually those oldest ones move off my plate. So we're spending this time on this analogy because the choice that you make, how will you eat the pancakes, will determine the age of pancakes left on your plate. So if you always eat from the top, the old pancakes are just going to keep getting older. If you always eat from the bottom, you're going to end up with a stack of pancakes that approaches some steady state profile of age. If you do something more complicated, you get a more complicated age of pancakes distribution. Now, instead of pancakes on a plate, let's think about those as water in a catchment. Instead of taking a bite, let's think of water flowing out of our catchment through the stream, or flowing out of our study reach through the stream. And instead of a crepe being added, let's think about that as inflows to our study reach. So what StorAge selection is going to do is essentially tell us about how is the water in our system being added to and exported from our study reach. Now here's an image out of Kieran Harmon's paper. So you can imagine these colored bars represent water stacked up from the oldest in blue to the youngest in red. And the idea of these three illustrations is to show you what happens if you eat pancakes equally from every age group, or pull your discharge equally from every age group. The Dirac delta function, in this case, is only sampling the oldest water. That's the equivalent of only eating the bottom layer of your pancakes. And on the right, a gamma distribution by which you eat mostly fresh young crepes, but somewhat eat those old pancakes too. So a more complicated distribution. And so while the StorAge selection module here on HydroLearn, as well as the manuscripts on this topic, go into a lot of detail, I want to show you how you can take the essential concepts and apply them to our solute tracer. where our tracer can actually help us understand which water did we sample, which water did we not sample, how old was the water that we were able to sample. Did we get really young, really fast flow paths? Did we get only really old ones, some blend in between? That's something that we'll be able to suss out by using this approach. All right, 4 essential concepts. The first is what's called the forward transit time distribution, and that's a lowercase p with a subscript q. And I'm picking these variables because they go along with the paper from Harmon that's linked in the resources for this module. So this represents a probability distribution. So PQ plotted through time in orange on the right-hand side. And what this is telling you is the probability that something you input at time 0 leaves at some time t. So for example, where this distribution peaks, that's the most probable age or the most probable time scale that the water would spend in our study reach. And again, this is normalized so that the area underneath that curve is equal to 1. Capital P sub q is simply the cumulative form of what we just described. And so in this case, capital T represents the age of water in the system. And the cumulative form is asking how much water is younger than time t, or what fraction of water is younger than t. And so far out here on the right-hand side, when this gets up to a value of 1, what that tells you is there is only water younger than that time scale. No water is older. When you're out here on the left at 0, what that's telling you is all water is older than that time scale. So that might represent the plug flow through a system, for example. Water just can't get through the stream channel faster than some advective time scale. Okay, so these have to do with how old the water is that's leaving our system, or how long water has spent in our study reach. Concept 3 is age-ranked discharge. And all we're doing here is taking the discharge we already know, Q, and multiplying it by that cumulative distribution, PT. And what this does is the exact same interpretation as concept 2 from the previous slide, but instead of having it in units of probability, you're starting to assign this to physical quantities. So instead of us asking what fraction of water is younger than a certain age, we can now say what fraction of the discharge is younger than a certain age. So what fraction of my discharge is entered the reach less than a day ago? What fraction of my discharge entered the reach more than a day ago? These are questions you can answer with the idea of age-ranked discharge. Now, note a couple of items shown in pink. There's probably some offset here where there is no discharge that is coming instantaneously fast. In other words, if this is a study reach, it takes some time to flow from the upstream end to the downstream end. And so in that case, none of your discharge is younger than that time scale for plug flow through the system. And there's probably also some maximum indicated up in the top right, where there's no flow coming from water that's older than a certain age. In other words, all of the water has some age to it. None of it is infinitely old. And just like we could relate this to discharge, where we ask ourselves, what fraction of my flow is from water younger than age t? We can also relate this to storage. So, well, step 3 is about the fluxes of water out of our catchment. It doesn't tell us much about the pancakes on the plate. It doesn't tell us what's left in the system. And so age-ranked storage, we can calculate as shown here. And what this is telling us is what volume of water within my study reach is younger than age t. And you get a similar distribution here, where with the knowledge of how much volume of water or how much storage is in your basin, you can start to line up your storage. And so you could imagine taking every parcel of water stored within your system and lining them up from youngest to oldest. That's essentially what this curve represents, with the youngest being first in line and the oldest being last in line. So you've got these 4 quantities to calculate, and all of it starts with that normalized breakthrough curve, step 1 that I showed you on the previous slide. Now, with these 4 quantities in hand, we can actually use these to make a plot that's much simpler to interpret. So on the x-axis, we're going to plot something about storage. We're going to plot 1 minus storage, or the storage complement. And on the y-axis, we're going to plot 1 minus that AgeRanked discharge, or the AgeRanked discharge complement. And our curve should look something like this. And what we can do, sort of based on these horizontal lines, we can see what the total discharge in our system would be. And we can see that there is some point at which there was water flowing out of the system, but we were not able to label it with our tracer. So not 100% of the discharge got labeled. Some of it's unlabeled. That's fine. That's water that was in the system before we put in our tracer, but it flowed out with our tracer. Similarly, where you are on the x-axis can tell you something about what storage did you see. So for example, storage to the left of that vertical dash line, so where I've just written in green, that's storage that is too old to be measured. In other words, that's beyond the window of detection for your tracer study. Storage that you actually measured with your tracer, highlighted in the brighter green color, and then in the purple, some volume of stream flow for plug flow, or some storage that is too young to have been measured will exist. So these are doodles on the screen. This diagram actually made its way into a recent publication. And so I encourage you all to check out this publication in HES. It is linked in the resources for this HydroLearn module. And the idea here is to help you understand not just how to calculate, but also how to interpret your storage selection analyses. So again, this recording is meant to be something of a boot camp to get you through just the bare essentials that you need to do a storage selection analysis. I strongly encourage you to check out the entire HydroLearn module on this topic if it's something that you're interested in. All right, next thing up is for you to try this with the data that we've been working with on this module. Thanks, everybody.